Hello guys and welcome back. So we are doing the organic chapter, that is haloalkanes and haloalkanes. So far in this chapter we have learned about nomenclature, we have learned about preparation of organic haloalkanes and also haloalkanes. After that we covered the physical properties of haloalkanes. Next we started with chemical properties of haloalkanes. Under the chemical properties, we have discussed substitution reactions. Yeah, we discussed substitution reactions where substitution with KOH leads to the formation of alcohol, so on and so forth. We did a number of substitution reactions. Now, the substitution reactions that we studied, okay, can be categorized into two types. What are those? Substitution nucleophilic bimolecular, that we write as SN2, and substitution nucleophilic unimolecular, that we write as SN1. Okay, first we will discuss in detail about SN2 reactions. Okay, so what is SN2 reaction? Since we are doing substitution reactions of alkyl halide, I'll start with the alkyl halide, say CH3Br, that is methyl bromide. Okay, now when we were doing substitution reactions, we had taken aqueous potassium hydroxide, where OH minus, okay, was the nucleophile. So I'm simply writing OH minus here, which is the nucleophile. Yeah? So the expected product is CH3OH, that is the alcohol, plus Br minus. So this will be the leaving group, that means it goes away. Now, what happens in this reaction? In this reaction, the rate of reaction is given as, where K is a constant, it will depend on concentration of CH3Br, that is the alkyl halide, and OH minus, that is the nucleophile. Okay? Since the rate depends on the concentration, this square bracket terms are concentration that you have learned in equilibrium chapter in class 11. So, since the rate depends on the concentration of the alkyl halide as well as the nucleophile, we will call it bimolecular reaction. Now, the term rate and this entire thing, this expression, you will understand better when we do the chapter chemical kinetics. Okay, for now you just understand that rate of the reaction, if it depends on the concentration of the alkyl halide and the nucleophile, it will be called bimolecular. Done. So this is bimolecular reaction. Let us see how the mechanism takes place. Okay, so this one I'll choose ethyl bromide, okay, and we will write the three-dimensional structure. CH3CH2Br. This is ethyl bromide. This is the dashed bond. We know that the dashed bond represents that this hydrogen is, on behind the black bond. This wedge bond represents that this hydrogen is towards me, that is towards the observer. What happens is, the nucleophile, that is OH minus, comes from behind and attacks this carbon, which is in a direction which is opposite to the bromide, Br minus. So after the attack takes place, there is a formation of transition state. There is a formation of transition state. How? CH3 ... Br ... OH, and you have that H here, and you have the H here. Okay, that is the dash bond. So we have this. So here the OH is also carrying delta negative charge and here is also carrying delta negative charge. In this is called the transition state. Okay, and in this transition state, both bond making and bond breaking is taking place at the same time. Okay, both bond making and breaking is taking place at the same time. What is our product? Since the nucleophile comes from behind and attacks the carbon atom from behind, there is the molecule flips. Okay, the molecule flips, and what happens is this hydrogen which was on the side will come this side. So we have OH, CH3. This will come here, H and H. Okay, plus Br minus. This is our leaving group. This is our leaving group. Now, this particular statement that I have used, that the molecule flips, okay, this is known as inversion of configuration, and about inversion of configuration we will learn in detail when we will do optical activity. Okay, so I hope this one is understood, that there is a backside attack and bond breaking and bond making takes place at the same time. Since the transition state depends on the concentration of both alkyl halide and the nucleophile, that is why this reaction is also called concerted reaction. Concerted reaction, meaning these two things are happening at the same time. And since the concentration of both are involved, so it becomes a bimolecular reaction. Okay? So under this, we have to discuss, okay, one more thing. So this flips, I made a mistake, this flips and it becomes, this will come here. So this will be like that and the dash bond comes here. So there is a flipping. Okay, there is a flipping. As you can see, this will come here. This inversion we will study in detail later. So this is about SN2. Now, one thing you must remember that SN2 reactions, are facilitated by polar, when you take the reactions in polar aprotic solvents. Polar aprotic solvents. Then this much for SN2. Next, example of polar aprotic solvents also I will give you. Okay, 1 minute. First we will discuss about reactivity. Next, reactivity of alkyl halides towards SN2 reactions. Reactivity of alkyl halides towards SN2 reactions. Now, first of all, let me start with methyl halide, that is CH3Br. Then we have ethyl, CH3CH2 H2Br. This is primary alkyl halide. After that we have CH3H and Br. This is secondary alkyl halide. This is isopropyl bromide. Next we have CH3 and Br. This is tertiary butyl bromide. Done. Now, if you look at all these alkyl halides and you need to think about substitution by a nucleophile in this alkyl halide. I have mentioned that the nucleophile will make a backside attack. So, if you think about OH minus coming and attacking here, OH minus coming and attacking in this carbon, OH minus coming and attacking in this one, and OH minus coming and attacking in this carbon. Okay, in which case do you find that there will be a maximum crowding of bi-alkyl groups? That is in the last case. Okay, that is in the last case. This methyl groups are causing crowding and not allowing the nucleophile to approach the carbon to which the halogen is attached. This crowding, okay, is known as steric hindrance. Is known as steric hindrance. Due to this reason, the order of reactivity of alkyl halides towards SN2 reaction is methyl is greater than primary, greater than secondary, and greater than tertiary. Okay, so the order of reactivity is methyl will be most methyl, that means methyl halides will be most reactive than primary, then secondary, and then tertiary. Okay, this is about SN2. Let's do about SN1. Okay. Now, SN1 reactions, that is substitution, nucleophilic, unimolecular. Let me take an example. CH3, 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 Br plus OH minus. This is tertiary butyl bromide plus OH minus. Expected product is tertiary butyl alcohol, CH3CH3OH plus Br minus. That is the tertiary butyl alcohol plus Br minus. In this case, the rate of the reaction is written as K is equal to K into concentration of CH3 whole thrice CBr, tertiary butyl bromide. That means the rate of the reaction depends only on the concentration of the alkyl halide and not on the nucleophile, only on one of the reactants. So it is unimolecular. Clear? Now, interestingly, SN1 reactions proceeds in two steps. Let's see how. In step 1, we start with the alkyl halide. Okay? We start with the alkyl halide and it forms the carbocation. Plus Br minus. This is the slow step. In the second step, this carbocation is attacked by the nucleophile. Okay, is attacked by the nucleophile. So we get CH3, CH3, and OH. That is tertiary butyl alcohol, and this is the fast step. Okay, this is the fast step. Now, in kinetics, we have to remember that the slow step is the rate determining step. And since in this step only one reactant is involved, that is why SN1 reactions become unimolecular. I am telling you again and again that these things will become more clear when we do kinetics. Just for now you must remember that in SN1, step 1 involves formation of carbocation and step 2 involves attack of the nucleophile to the carbocation. Yeah? So this is the mechanism. Let's see the order of reactivity. Now, reactivity of alkyl halides towards SN1. Okay, reactivity of alkyl halides towards SN1. Now we know that SN1 reactions proceeds with the formation of carbocation. Clear? Proceeds with the formation of carbocation. So I'll start with methyl carbocation, CH2, CH3 ethyl carbocation. Then we have, I'll write this here, isopropyl carbocation and tertiary butyl carbocation. Done? Now, this is primary carbocation, secondary and tertiary carbocation. If you remember from your knowledge of class 11, we had studied the order of reactivity of carbocations. And we know that methyl groups are electron donating groups. So in tertiary carbocation, we have 3 methyl groups which are donating their electron density towards this carbon which is electron deficient. So naturally, the tertiary carbocation becomes more stable. If it becomes more stable, this will react in a faster way. So the order of reactivity is tertiary greater than secondary greater than primary. So the order of reactivity of alkyl halides for SN1 is 3 degree greater than 2 degree greater than 1 degree. Okay, and the last piece of information that I want to give you here is for SN1 reactions, polar protic solvents facilitate the reaction. Polar protic solvents like water, then you have acids like H2SO4, and for SN2, this is SN1 and SN2 is polar aprotic solvents. Okay, like acetone, then dimethyl sulfur oxide, DMF, okay, etc. Now, these are something which I will explain in notes and in your online sessions. This is theory based, nothing much to learn. You have to remember the mechanism, you have to remember the order of reactivity from this section. Okay, so with this, I'll conclude the lecture about SN1 and substitution nucleophilic, unimolecular and bimolecular. I hope you follow the video, follow the notes, exercises with this will also be there. Okay? Thank you everyone.